Welcome back to the deep dive. Today we're doing something a little bit different. Usually we take a specific company or maybe a new piece of hardware and we tear it apart. But today we are zooming out, way out. We are looking at the entire tectonic plate of the global automotive industry. And frankly, that plate is shifting.
It really is. And it's shifting in a way that I don't think the average consumer or even the average investor fully grasps yet. If you have been following the headlines for the last, say, 5 years, you have a very specific narrative drilled into your head.
Right. The narrative is super simple. The internal combustion engine, the ICE, is dead. It's a dinosaur. Batteries are the singular future. And the transition is just this straight line up and to the right. Everyone buys an EV, the air gets clean, and we all live happily ever after.
Exactly. That was the simple transition narrative. It was clean, it was linear, and, it was really easy to put on a PowerPoint slide. But the stack of reports we are breaking down today, and we are talking about heavy-duty strategy audits, technical papers from the AECC, and market analysis for the 2024 to 2026 window, they are telling a very different story. They are calling it the Great Recalibration.
The Great Recalibration. That sounds like a very polite corporate way of saying we got the math wrong.
Or at least we got the timeline and the sheer complexity of the ecosystem wrong. We are seeing a massive shift from a strict BEV-only ideology to something the experts in these reports are calling technology neutrality. The data suggests the future isn't just about batteries anymore. It's about a really complex ecosystem of advanced engines, synthetic fuels, digital twins, and batteries all working together.
So our mission today is to act kind of like management consultants. We aren't just car enthusiasts today. We are, McKinsey analysts. We are going to perform a top-down strategy audit on this entire carbon-neutral paradigm shift. And the reports introduce a concept right off the bat that I think frames this perfectly. They call the current market state stagflation.
Stagflation, yeah, it's a portmanteau that is absolutely keeping auto executives up at night right now.
It sounds like a terrible medical condition. Like, I'm sorry to tell you, but you have acute stagflation.
It definitely feels like one for the industry. It stands for stagnation plus transformation. Here is the paradox they are facing. Production volumes globally are flatlining. There is no new massive growth in sales numbers, so the pie isn't getting any bigger, but at the exact same time, the regulatory pressure to completely transform the technology stack, things like Euro 7 and EPA 2027, is higher than it has ever been.
So basically, no new money is coming in from sales growth, but you are being forced to spend billions of dollars in CapEx to reinvent the entire machine.
Precisely. It is the worst of both worlds. And that extreme financial pressure is exactly what breaks that simple transition narrative we talked about. You can't just throw venture capital money at problems anymore because the margins are being squeezed so tightly. You have to be surgical. You have to look at life cycle assessment or LCA, and you really have to look at supply chain risk.
Okay, so to keep us from getting totally overwhelmed by the engineering jargon, because there is a massive amount of it in these sources, we are going to break this down using a structured audit. We're going to use a MECE framework, mutually exclusive, collectively exhaustive.
Look at you speaking the high-level consultant language already. I love it.
I try my best. So here's the roadmap for you listening. First, we'll cover the macro drivers, the geopolitics, the supply chains, the why of it all. Why is the global market fracturing? Second, the core strategy. This is where we get into that life cycle assessment and why the math on emissions is fundamentally changing. Third, the technical execution, the actual nuts and bolts of how you build a hybrid engine that physically cleans the air. And finally, digital compliance, which sounds suspiciously like Big Brother watching your tailpipe.
Which, spoiler alert, is exactly what it is. The car becomes a data node, but we will get to that.
Can't wait. So let's start at the very top, the macro drivers. The sources describe a world that has totally fractured. It's not a global one-size-fits-all car market anymore. It's three distinct zones playing three very different strategic games.
Right. This is the geopolitical layer of the audit. You have North America, Europe, and China, and their strategies are diverging incredibly rapidly.
Let's start with Zone 1 North America. The reports call this zone the pragmatic balancer. What does that actually mean in practice? Is that just a nice consultant-speak way of saying they're dragging their feet on EVs?
Not exactly dragging their feet. It means they are ruthlessly driven by the bottom line. Look at the U.S. market right now. The battery electric vehicle, the BEV growth curve, is flattening out. It is not crashing entirely, but that exponential hockey stick growth is just gone. And the main reason is high interest rates.
Because money is expensive right now.
Exactly. When interest rates are hovering around 6 or 7%, the monthly payment on a $60,000 electric truck becomes absolutely astronomical for normal people. So the average consumer is just saying, no thanks, I'll hold off.
So what do the automakers do then? They can't just pause the assembly lines and stop selling cars.
They pivot right back to what protects their profit margins. Huge trucks and midsize SUVs. But, and this is the key difference, they aren't just building the old gas guzzlers of the 1990s anymore. We're in the middle of a massive hybrid renaissance.
A hybrid renaissance. So basically, slapping a small battery onto a traditional V6 engine.
Essentially, yes. It is a pure profit protection strategy. They are reserving the ultra-high-tech, super expensive 800-volt electric architectures only for the massive halo vehicles where you absolutely have to solve range anxiety, the heavy trucks, the luxury SUVs. For everything else in the middle, the daily drivers, it is hybrid. It is about balancing the upfront cost for the consumer with the necessary profit margin for the factory.
So for North America, the winning formula is keep the combustion engine, add a battery to help with efficiency, and protect the margin at all costs.
Correct. Now, contrast that entirely with Zone 2, which is Europe. The reports label Europe as the defending innovator.
Defending against what exactly?
Against irrelevance, and frankly, against the Chinese supply chain. Europe is in a very difficult, very defensive spot. Their strategy is entirely driven by regulations, specifically the incoming Euro 7 standards and this new concept called the Clean Industrial Deal. They are terrified of supply chain dependency.
This is where the whole rare earth mineral discussion comes in, right? Because we constantly hear about how China essentially owns the rocks in the ground.
Yes. And the European response to this is fascinating because it is a pure engineering solution to a geopolitical problem. There is a technical detail in the AECC source material about electric motors that we really need to unpack. Europe is shifting aggressively to a technology called ESM.
EES. Okay, let's break that acronym down because right now it just sounds like a random collection of letters.
It stands for Externally Excited Synchronous Machines.
That is quite a mouthful. What does it actually do differently than a normal EV motor?
To understand an ESM, you first have to understand how a normal, standard EV motor works. Most electric motors today, like the ones you'd find in a Tesla Model 3 or a BYD, they use permanent magnets.
Like the magnets on my fridge, but obviously much stronger.
Much, much stronger. They are made with heavy rare earth metals like dysprosium, terbium, and neodymium. These are incredibly powerful, naturally occurring magnets that sit inside the motor and force it to spin when electricity is applied.
And let me guess, Europe doesn't have any massive dysprosium mines sitting around.
No, they don't. China controls something like 90% of the global refining capacity for those specific heavy rare earths. So if you are a European automotive CEO sitting in Munich or Paris, and you base your entire corporate future on permanent magnet motors, you are basically handing the keys to your entire supply chain over to a geopolitical rival. If trade relations sour even a little bit, your assembly line simply stops.
So this ESM technology is the European workaround.
It is the ultimate workaround. Instead of using a permanent rare earth magnet rock, European engineers are designing motors that use tightly wound copper coils on the spinning part, which is the rotor. They run electricity from the battery through that copper to artificially create a magnetic field on the fly.
So they're just turning a massive electromagnet on and off.
Exactly. They are replacing geological advantage with applied physics.
Is it actually as good as the rare earth version?
It is different. It is slightly heavier because of all the copper you have to use, and it is definitely more complex mechanically because you need special brushes or a wireless induction system to get the electricity into the part of the motor that is physically spinning. But, and this is the massive strategic win, it is entirely rare earth free. It creates what the EU calls strategic autonomy.
That is wild. It is literally engineering driven entirely by foreign policy. They're saying, we can't safely buy your rocks, so we are going to redesign the physics of the motor.
Precisely. And it actually has a really cool side benefit. You can turn the electromagnet completely off when the car is just coasting down the highway, which makes it far more efficient at high speeds. A permanent magnet is always on, so it is always creating a tiny bit of magnetic drag.
Right.
ESM eliminates that.
Okay, so that's Europe. Regulatory defense and deep supply chain paranoia. Now let's look at Zone 3, China. The reports call them the aggressive integrator.
This is undoubtedly the most dynamic zone in the world right now. While Europe is playing defense, China is vertically integrating everything. They control the mine, the refining process, the battery cell manufacturing, and the final car assembly. They own the whole stack.
But I read something in your notes on the report that honestly surprised me. I always thought China was the promised land of the pure battery electric vehicle. But the data says they're actually moving heavily toward hybrids too.
They are, but it is a very different kind of hybrid than what we see in North America. They are seeing a massive surge in PHEVs, which are plug-in hybrids, and EREVs, which are extended-range EVs.
Wait, can you distinguish those two for me?
Okay.
What is the actual mechanical difference between a PHEV and an EREV?
Sure. A plug-in hybrid, a PHEV, physically connects the gas engine to the wheels, so it can drive exactly like a normal gas car when the battery is completely empty. An ERV, an extended-range EV, is fundamentally different. The wheels are only ever turned by the electric motor. The gas engine is just an onboard generator. It sits in the back, totally unconnected to the wheels, just humming along at its most perfectly efficient RPM, solely to charge the battery.
So it's literally just an onboard power plant.
Exactly. And the reason they are pivoting to this is because Chinese automakers are now building cars with 2,000-kilometer ranges.
2,000 kilometers. That's like driving from New York to Florida without stopping for fuel once.
You simply cannot do that with a battery alone. The energy density of lithium-ion just isn't there. If you tried to build a battery pack that could go 2,000 kilometers, the car would weigh 4 or 5 tons and cost a fortune. So even the market that completely owns the global battery supply chain, China, is openly admitting that we still need an internal combustion engine if we want to solve the range problem for the average consumer.
That brings us really neatly to the second macro driver in our audit: supply chain vulnerability. We touched on the rare earths, but the reports also talk a lot about this concept of anti-fragility.
Right. This is where the management consultant view really comes into focus. If you are a car company CDO right now, you are staring at a historical chart of lithium carbonate prices. And it looks like an EKG of someone having a heart attack.
It bounces around that drastically.
It is incredibly volatile. It shot up from around $10,000 a ton to over $80,000, and then crashed all the way back down. The current forecasts suggest prices might rebound to maybe $16,000 a ton by 2026. But the absolute price isn't the problem. The volatility is the killer.
Because if you operate a car company on razor-thin single-digit margins, you literally can't predict what your product will cost to build next year.
Exactly. If you bet 100% of your company's future on batteries, and lithium spikes 20% because of a mine strike in South America or a random trade war tariff, your entire profit margin for the year just evaporates. This is why the AECC's concept of technology neutrality is gaining so much traction in boardrooms. It is not just an emission strategy anymore, it is a core risk management strategy.
So holding on to the internal combustion engine and developing advanced hybrids isn't just automakers being stubborn or resistant to change, it is a financial hedge.
It is an insurance policy. If you have hybrids, e-fuels, and pure EVs all balanced in your portfolio, you can pivot dynamically. If lithium prices spike, you push your marketing to sell more hybrids. If the power grid in a region is unstable, you push e-fuels. If you only have EVs, you are completely exposed to single points of failure.
That makes perfect sense. It's way less about technological ideology and way more about basic corporate survival.
Welcome to the Automotive Boardroom in 2026.
Okay, let's move into Section 2 of our MBCE framework, the core strategy. This is where the reports get a bit controversial, or at least they push hard against the mainstream narrative. They outline a massive regulatory pivot from tailpipe emissions to LCA.
This is arguably the most important paradigm shift for you listening to understand today. It completely changes how regulators and the industry keep score. For 40 years, the word clean meant one very specific thing: nothing coming out of the exhaust pipe.
Tank-to-wheel accounting.
Correct. If the tailpipe was clean, the car was legally classified as zero emission. It did not matter if you had to burn a literal forest down to generate the electricity, or if the factory that built the car was powered by dirty coal. The car itself got the zero emission halo.
But the science and now the European regulations are saying, wait a minute, that is fundamentally bad accounting.
It is terrible accounting. You have to look at the entire life cycle, cradle to grave. You have to count the carbon emitted when you mine the raw lithium, when you ship the heavy ore across the ocean on diesel cargo ships, when you refine it, and crucially, when you bake the battery cells in massive industrial kilns at super high temperatures.
And when you actually do that math, the picture changes pretty drastically, doesn't it?
It totally flips the script.
Yeah.
The source material from the ACC is very blunt about this. A battery electric vehicle starts its life with a massive carbon debt.
A carbon debt. Explain how that works in practice.
Think of it like a massive credit card balance. When a traditional gas car rolls off the assembly line, it has a relatively small carbon debt. It's mostly just the energy it took to stamp the steel and mold the plastic. But when a long-range EV rolls off the line, it has a huge carbon debt because battery manufacturing is incredibly energy intensive. It is starting the environmental race 50 meters behind the gas car.
So it has to drive for a long time just to catch up to the baseline.
Exactly. It has to drive a lot of clean, zero tailpipe miles just to pay off that dirty manufacturing debt. The life cycle data shows it takes thousands and sometimes tens of thousands of kilometers of driving just to break even with a standard, highly efficient combustion engine car.
And what if you don't drive that far? Or what if you plug it in every night on a local power grid that runs on coal?
Then you might literally never catch up. If you buy a massive heavy EV truck with a huge battery and you only drive it 5 miles to the grocery store once a week and you charge it on a fossil fuel heavy grid, you have actually emitted more total carbon into the atmosphere than if you had just bought a small, efficient diesel hatchback.
Wow. That is genuinely painful to hear. It feels a bit like the public has been sold a bill of goods on the EV revolution.
It is not that EVs are bad. They are excellent pieces of technology if they are utilized correctly in the right scenarios. But they aren't magic. They are physical objects governed by thermodynamics. And this is exactly where the AECC, the Association for Emissions Control by Catalyst, comes in with some really compelling empirical evidence. They partnered with Green NCAP to do a massive life cycle assessment study.
This is the study comparing the C-segment cars, right? Like your standard Volkswagen Golf size.
Yes, they took a totally standard, average commuter car size and compared it across multiple different powertrains using this strict cradle-to-grave accounting math. We should really walk through the specific numbers here because they are startling.
Go for it. Lay out the data.
First, they modeled a pure battery electric vehicle, and they gave it the absolute best-case scenario. They assumed it was charged exclusively on pure wind energy for its entire life. The result was 60 to 70 grams of CO2 equivalent emitted per kilometer over the entire life of the car.
Okay, so 60 to 70 grams. That is the gold standard benchmark we were trying to beat.
Right. Then they modeled a modern internal combustion engine car, but instead of filling it with fossil fuel, they ran the simulation using HVO.
HVO, remind me what that stands for.
Hydrotreated vegetable oil. It is basically incredibly high-tech, highly refined waste cooking oil and animal fats. They also ran the numbers with e-gasoline, which is a fully synthetic fuel.
And what was the carbon footprint result for the combustion engine?
60 to 70 grams of CO2 equivalent per kilometer.
Wait, so it's exactly the same. It's a tie.
It is a statistical dead heat. A modern combustion engine running on a renewable, sustainable fuel is just as clean over its total lifetime as an electric car running exclusively on wind power.
That fundamentally destroys the narrative that the physical engine itself is the enemy of the climate.
That is exactly the primary takeaway for any policy consultant looking at this. The enemy is not the machine. The pistons and cylinders are fine. The enemy is the fossil fuel. It's the energy carrier that is the problem. If you simply change the chemical makeup of the carrier, you immediately save the machine and the millions of jobs tied to manufacturing it.
Okay, but I have to play devil's advocate here for a second. I am looking at the notes on primary energy demand, or PED, from the report. It explicitly says that manufacturing these e-fuels is incredibly inefficient, right?
Oh, absolutely. You have to be totally honest about the thermodynamic reality here. Making synthetic e-fuel is very hard, energy-intensive work. You have to physically capture carbon dioxide out of the ambient air. You have to use massive electrolyzers to split hydrogen out of water. And then you have to mash those two elements together under high heat and pressure using huge amounts of renewable electricity. The PED is really high. It takes about 2.2 kilowatt hours of raw energy just to create enough synthetic fuel to drive a car 1 single kilometer.
And how does that compare to just putting that electricity straight into an EV?
A standard EV uses about 0.7 or 0.8 kilowatt hours to go that same kilometer. So if you are looking strictly at the raw energy input, the EV is roughly 3 times more efficient.
So if it takes 3 times more energy to make a gallon of e-fuel, why would we ever bother? Why not just build more power lines and put all that green electricity straight into batteries?
Because of energy storage density and heavy-duty applications, raw efficiency isn't the only metric that matters in the real world. Density is everything.
Give me a practical example of where density beats efficiency.
Take a long-haul semi-truck that needs to cross the Australian outback or the American Midwest, or think of a massive heavy-duty excavator operating in a remote lithium mine in northern Canada. You simply cannot put a battery in that excavator. To hold enough charge to last a full 12-hour shift moving tons of earth, the battery pack would need to be the size of a small house. The volumetric energy density of current batteries just isn't remotely close to being viable for that.
But liquid fuel?
Liquid molecules are the absolute ultimate energy storage device. They are incredibly dense, they are chemically stable for months or years, and you can easily transport them in a cheap metal tank to anywhere on Earth. So the overarching strategy coming out of these think tanks is becoming use electrons where you can, but use molecules where you must.
Electrons where you can, molecules where you must. I really like that framing. It feels balanced. It feels, well, technology neutral.
That is the ultimate goal of the AECC. But achieving that philosophy requires a completely different technical approach from the automakers. The industry can't just throw all their R&D budget at solid-state batteries anymore. They have to run what the reports call a dual-track execution strategy.
Which perfectly transitions us to Section 3 of the audit, technical execution. This is the actual hardware, the physical nuts and bolts of the transition.
This is where the mechanical engineers really earn their paychecks. Because keeping the combustion engine alive in this new regulatory environment isn't about just slightly tweaking the old engines. It is about building a fundamentally radically new machine from the ground up.
So walk me through track 1 of this dual strategy. The notes say this is focused entirely on zero-impact pollutants.
Right. This track is directly driven by the incoming Euro 7 standards in the EU. The stated goal here is almost poetic in its ambition. They want to make the exhaust coming out of the tailpipe physically cleaner than the ambient air the car is driving through in a polluted city.
I have definitely heard that claim before in car commercials, like, this car cleans the air as you drive it. Is that actually an engineering reality now, or is that just marketing fluff?
With the specific new hardware mandated by Euro 7, it is actually becoming a measurable reality. But the biggest engineering challenge isn't when the car is cruising at highway speeds with a warm engine. The critical failure point is the cold start.
Right, like starting your car on a freezing winter morning at -7 degrees.
Exactly. Catalytic converters, those expensive ceramic honeycombs hidden inside your exhaust pipe that actually scrub the toxic pollution. They are essentially complex chemistry sets. And like most complex chemistry, the reactions simply don't happen until the catalyst is incredibly hot. We are talking 200 to 300 degrees Celsius before they wake up.
So when the engine block is freezing cold.
The chemical scrubber is completely asleep. In the first 20 to 30 seconds of a cold drive, a standard car will spew out the vast majority of its toxic pollutants for the entire trip.
So how do you fix that? You can't regulate the winter weather away.
No, but you can turn the exhaust pipe into a high-powered toaster.
A toaster?
Literally. The engineers are installing a piece of hardware called a 48-volt electric heating catalyst, or EHC. It is a powerful electric heating element, basically a specialized metal disc mounted inside the exhaust pipe right directly in front of the ceramic brick. The moment you unlock the car, or within a fraction of a second of hitting the start button, it blasts the catalyst with intense electric heat.
So it preheats the chemical scrubber before the engine even makes any dirty exhaust.
Yes. It gets the core up to operating temperature in less than 5 seconds, down from 20 or 30 seconds in a traditional car.
So by the time you put it in gear and actually back out of your driveway, the scrubber is already 100% active.
Precisely. This electric heater is effectively going to be mandatory for Euro 7 compliance. But they aren't stopping there. They are totally changing the physical architecture of the exhaust system itself. They are moving to what is called a split architecture.
What does a split architecture look like under the car?
Imagine having two totally separate scrubbing systems. The first one is called close-coupled. It is jammed right up tight against the engine block. Why? To instantly catch that initial intense burst of heat right out of the combustion chamber. The second system is mounted underfloor, much further back along the chassis, and it is specifically tuned for high-speed, high-load driving.
Why do you need the second one? Wouldn't the one near the engine catch everything?
Because if you are driving incredibly fast, say wide open on the German Autobahn, that close-coupled scrubber might actually get far too hot and lose its chemical efficiency. By splitting them up physically, the car's computer can perfectly manage the chemistry across every possible driving speed. This dual setup can scrub dangerous nitrogen oxides, or no NOx, down to incredibly low levels. We're talking less than 100 milligrams per kilowatt hour. That is practically microscopic.
Okay, so we have completely scrubbed the tailpipe emissions. But the source has also spent a lot of time on something called non-exhaust emissions. This one honestly surprised me. The environmental regulators are coming for your brake pads.
This is often referred to as the silent killer aspect of the Euro 7 regulations. As the tailpipe exhaust gets cleaner and cleaner, the physical dust wearing off your brake pads and your rubber tires becomes a much larger percentage of the total pollution a car creates. And in a modern EV, because the battery makes the vehicle so incredibly heavy, brake and tire dust is a massive growing problem. Euro 7 regulates this brake dust, specifically PM10 particulate matter, for the very first time in history.
I have to admit, I never really thought about where the brake dust goes.
Yeah.
I just washed it off my wheels and assumed it vanished.
It definitely doesn't vanish. It goes straight into the local air and then directly into our lungs. It is highly toxic particulate matter. So the engineers are being forced to completely reinvent the common brake disc. They are moving away from cheap cast iron and towards tungsten carbide coatings.
Tungsten carbide.
Right.
Isn't it the ultra-hard stuff they use on industrial drill bits for mining?
It is. It is one of the hardest, most durable materials on the planet. They are using advanced lasers to coat the standard brake disc with a super thin layer of this ceramic metal matrix. The surface ends up being mirror smooth. It essentially never rusts, and it barely wears down at all over the life of the car.
And what does that do to the toxic dust output?
It reduces it by an astonishing 90%.
90%. That is a massive public health win. But surely applying industrial lasers and tungsten to a family car is incredibly expensive.
It is hugely expensive. A tungsten carbide coated brake disc costs roughly 3 times more to manufacture than a standard iron disc. This single regulation turns the entire economics of brake engineering completely upside down. It used to be a cheap, heavy commodity part that you replaced every few years. Now it is a permanent, high-tech piece of hardware.
And I assume this intense focus on particulates applies to all those massive excavators and farm tractors too.
Oh.
What the reports call non-road mobile machinery, or NRMM.
It absolutely does apply to them, but those machines have a very unique, separate problem. They suffer from what engineers call the low-load problem.
What exactly is a low-load problem for a tractor?
Imagine a massive diesel excavator sitting on a construction site, just idling, waiting 10 minutes for the next dump truck to arrive. The massive engine is technically running, but it is barely doing any physical work. Because it isn't working hard, the exhaust gas temperature plummets. If that temperature drops below 200 degrees Celsius, the chemical scrubbers, specifically the selective catalytic reduction or SCR system, they just physically stop working. The chemistry halts.
So a heavy excavator just idling in neutral is actually polluting far more than one doing heavy lifting, just because the exhaust is too cool.
Exactly. It creates a massive thermal deficit in the system. The engineering fix for this is, again, forced active heating. The Tier 5 compliance notes explicitly state that a massive 5 kilowatt electric heater is the new threshold. If you do not have 5 solid kilowatts of electric heating power available to instantly blast the exhaust, you simply fail the compliance tests. The old passive systems where you just wrap the pipe in insulation, they just can't cut it anymore.
That is incredible. The level of engineering going into just the exhaust pipe is staggering.
So that's track 1, cleaning up the physical pollutants. Now track 2 is the big macro one for global climate change, net zero greenhouse gases. This brings us to what the consultants are calling ICC 2.0. I absolutely love that the 100-year-old internal combustion engine is getting a Tech Bro software version number. Honestly, given the tech involved, it fully deserves it. We are currently watching a massive engineering race to hit 50% brake thermal efficiency. For context, a standard, decent car engine from maybe 10 years ago was only about 30 to 35% efficient. Hitting 50% efficiency is like breaking the sound barrier for thermodynamics.
How are they physically doing that? You can only compress gas so much.
They are borrowing heavily from Formula One racing. The reports specifically highlight a technology called TJI, or turbulent jet ignition.
Turbulent jet ignition. That sounds like a propulsion system from a sci-fi spaceship.
It really acts like one inside the engine. It relies on pre-chamber technology. Imagine a normal, traditional engine cylinder. You have a big open room filled with a mixture of fuel and air. A standard spark plug fires at the top, and a flame front spreads relatively slowly across the room. It works, but it is slow and leaves unburnt fuel.
Okay, I can visualize that.
Now, with TJI, the spark plug is totally hidden. It sits inside a tiny separate chamber, a little thimble-sized room sitting right above the main cylinder. That little room is injected with a very rich, highly concentrated mix of fuel. The spark plug ignites that tiny pocket first. Because the space is so small and confined, the pressure inside spikes instantly and violently.
And then what happens to all that pressure?
It shoots literal jets of superheated flame, essentially acting like a multi-directional flamethrower out of tiny nozzle holes directly down into the main cylinder. It doesn't just casually light the main fuel source, it completely blasts it from multiple angles simultaneously.
So instead of lighting a single match in a dark room, you are hitting the fuel with the plasma flamethrower.
Exactly. It forces the fuel to burn instantly and completely, even if the mixture in that main cylinder is incredibly lean, meaning it is mostly just air with very little actual fuel injected. That absolute maximum extraction of energy is how you push towards 50% efficiency. You are squeezing every last possible joule of work out of every single microscopic drop of fuel.
And this isn't just theory on a whiteboard anymore.
No, this is highly proven F1 technology rapidly moving down market into everyday passenger cars. And when you combine TJI with other massive innovations like variable compression ratio, where the engine block can physically change its internal geometry on the fly to squeeze the fuel harder when you accelerate, we are looking at the most advanced, efficient mechanical machines ever built by humanity.
But, and here's the ultimate kicker for this whole strategy. All of this amazing sci-fi hardware still fundamentally needs to burn fuel.
Yeah.
And if we just put regular crude oil gasoline from the corner station in it, it still emits fossil CO2 into the atmosphere.
Correct. And that is exactly why the entire technology-neutral strategy desperately depends on the rapid scaling of drop-in fuels. This is the absolute crucial bridge for the stagflation period we are in right now. We currently have hundreds of millions of combustion cars on the road globally. We cannot just scrap them all tomorrow and build EVs. It would bankrupt the world. But HVO, that high-tech vegetable oil we talked about earlier, can be used today, right now, in existing diesel fleets. You can fill up a 10-year-old delivery truck with pure HVO and boom, you have instantly decarbonized that specific vehicle's life cycle by up to 90%.
That seems like such an obvious, low-hanging fruit for fighting climate change. Why isn't every shipping company in the world doing it immediately?
It comes down to raw cost and supply availability. There just aren't enough waste French fries in the world to run global commerce. But the strategy audit suggests this biofuel is the necessary short-term bridge. And then, as we move toward 2030 and 2035, you transition to the fully synthetic e-fuel scaled by massive renewable energy grids. It is a phased approach.
Okay, so we have deeply covered the macro drivers and the physical hardware tech. Now we need to move to the enforcer. Section 4 of our MECE breakdown, digital compliance. This is the part of the report where the car basically starts watching your every move.
This is the massive regulatory shift from the controlled laboratory to the messy real world. We all vividly remember the Dieselgate scandal, right?
Oh, absolutely. It's hard to forget. Cars basically realizing they were strapped to a testing treadmill and secretly changing their engine behavior to pass the test, then polluting wildly on the real road.
Well, the global regulators definitely learned their lesson from that embarrassment. The era of testing a pristine prototype car once in a perfect, climate-controlled lab is permanently over. The future mandated by Euro 7 is OBM, onboard monitoring. The car is now required to check itself continuously every second it is running for its entire legal life. That means 160,000 to 200,000 kilometers of nonstop self-auditing.
So there is quite literally a permanent digital snitch living in your dashboard. How does that actually work technologically?
It relies on a concept called sensor fusion. First, you have highly sensitive physical sensors mounted inside the exhaust pipe, actively measuring NOx and particulates. But physical sensors operating in a hot, toxic exhaust pipe can eventually fail, or their accuracy can drift over time as they get coated in soot. So the software engineers are pairing those physical sensors with virtual sensors.
Virtual sensors, like imaginary software sensors.
Basically, yes. They are advanced AI models running locally on the car's computer. The engine control unit knows exactly how much fuel it is injecting. It knows the exact ambient air temperature, the barometric pressure, the engine load. It feeds all that raw telemetry into an AI model, specifically utilizing something called a mixture of experts architecture to calculate and predict exactly what the tailpipe emissions inherently should be at that exact millisecond.
And then it just constantly compares the real physical sensor data to the AI's perfect prediction.
Exactly. And to manage discrepancies, they use a highly complex mathematical tool called a Kalman filter.
A Kalman filter. Wow, I have not heard that specific term since my college statistics classes.
Well, it is making a massive comeback in automotive engineering. The Kalman filter dynamically blends those two data signals, the physical and the virtual. If the physical sensor suddenly starts reading something crazy and out of bounds, the Kalman filter analyzes the AI model and says, I don't trust the physical sensor right now. It must be dirty. I am sticking with the AI's calculated value to ensure compliance. It ensures the vehicle creates an unbroken, cryptographically verified record of its emissions every single second it is turned on.
And what actually happens if the car's computer realizes it is actively polluting over the legal limit? Say, I purposely tamper with the exhaust filter to get more horsepower, or I just refuse to refill the AdBlue fluid.
That is when the vehicle's inducement system aggressively kicks in.
Inducement system, that sounds incredibly ominous.
It is meant to be. It is legally designed to induce you, the driver, to immediately fix the non-compliant car. Depending on the severity of the violation, it can electronically restrict your top speed, forcing you to limp home, or in severe cases of tampering, it can simply prevent you from restarting the engine entirely once you turn it off.
Wow, it's literally like, I'm sorry, Dave, I can't let you drive this car today.
It is exactly like that. The car becomes the ultimate regulatory enforcer. Ideally, it just keeps the urban air clean. But here's where the AECC report suggests this technology gets really sci-fi. They introduce the concept of the green passport. The OBM system will eventually need to be smart enough to know exactly what kind of fuel you just put in the gas tank.
Because if I am paying $15 a gallon for perfectly clean synthetic e-fuel, I want the regulatory credit for being green.
Exactly. Right now, a combustion engine is completely dumb. It doesn't know if it's burning heavy dinosaur juice or pristine synthetic wind power juice. It just burns what is there. But future sensor suites will be designed to instantly detect the specific chemical signature or the digital tracer of carbon-neutral fuels.
And then what does the car do with that information?
The OBM system instantly credits your personal or corporate CO2 account. It immediately reports to the manufacturer's cloud server saying, hey, this specific vehicle is running on 100% green fuel right now. Log the carbon offset. It fundamentally turns environmental compliance from a mechanical hardware problem into a seamless software and data accounting problem. You could theoretically have a government tax break applied instantly to your bank account because your car cryptographically proved you used green fuel on your commute.
That is just a massive mind-bending integration of raw chemistry, mechanical hardware, and cloud software. It leads us perfectly into Section 5 of our outline, the policy integration and the actual timeline. Because none of this massive R&D spending happens in a vacuum. It is all driven by the deadlines.
No, it doesn't happen in a vacuum, and the timeline the EU has set is incredibly tight. We are officially on the critical path right now. By 2025, which is essentially tomorrow in automotive development years, the Euro 7 implementation acts get finalized and locked in. That is the final rulebook. Then, by November 2026, those strict rules apply to all new types of light-duty vehicles. And by May 2028, it hits the massive heavy-duty trucks.
So the global manufacturers are just scrambling right now to integrate all this.
They are frantically engineering and testing. And the overarching EU policy is officially shifting to what they call a one-package approach. They are finally trying to comprehensively balance clean air, meaning the local toxic pollutants like null tax, with climate change, meaning the global CO2 emissions.
And this connects right back to the geopolitical macro drivers we discussed at the start, right? The push for strategic autonomy.
100%. The European Union has painfully realized, especially after recent energy shocks, that it absolutely cannot trade its historical dependence on foreign oil and gas for a new, total dependence on Chinese battery supply chains. Keeping the highly advanced internal combustion engine legally alive via e-fuels and hydrogen combustion is a critical strategic way to preserve European industrial sovereignty.
It's a massive jobs program.
It keeps hundreds of thousands of highly skilled manufacturing and engineering jobs inside Europe. It keeps their historical technology base relevant. And to support this, the EU is rolling out significant financial levers. The reports highlight a massive €1.8 billion battery booster plan to try and aggressively spin up a localized European-owned battery value chain.
$1.8 billion is a lot of money, but against the scale of the global auto industry, is it really enough to catch up to Asia?
It is a start, but they're also pulling regulatory levers to free up more capital. The EU is proposing administrative simplifications that they project will save the industry around €706 million every single year in pure red tape costs. The explicit goal is that automakers take that $706 million in OPEX savings and immediately redirect it into decarbonization R&D. Furthermore, they are looking at demand-side acceleration. mandating that massive corporate vehicle fleets hit strict zero-emission purchasing targets to artificially guarantee market scale for these new technologies.
So they're forcing the big companies to buy the green cars first to drive the price down for normal consumers.
Exactly. And the rest of the world is watching this European experiment incredibly closely. The global ripple effects of Euro 7 and this tech-neutral approach are huge. For instance, India is currently implementing BS7, or Bharat Stage 7. The strategy reports indicate they will likely copy the Euro 7 framework very closely, but with a massive localized warning. Indian regulators know they absolutely must avoid the worst-case boundary conditions of Euro 7 to keep basic mobility affordable.
Meaning, they can't make the emissions regulations so incredibly strict and expensive that a standard middle-class family in Mumbai is entirely priced out of buying their first car.
Exactly. You have to balance climate goals with basic economic development. And over in the U.S., the EPA's Tier 5 regulation is focusing heavily on aggressively fixing that low load cycle problem we talked about for heavy machinery and long-haul trucking. The entire global regulatory apparatus is moving steadily toward this holistic system integration model.
So we've completed our strategy audit. We have looked at the geopolitical drivers, the staggering new hardware tech, the digital compliance software, and the incoming laws. Let's head to the final phase, the outro. As a top-tier management consultant, what is the ultimate so what for our listener today?
The primary so what is that the era of the simple transition is completely dead. The naive idea that we would just eventually swap a gas tank for a lithium battery on every car and call the climate crisis solved, that is gone. We have officially entered the era of hyper-complex system integration.
It's definitely not about searching for one single silver bullet technology anymore.
No, it is not. Corporate success in the 2030s now requires mastering 3 heavily overlapping circles of competence. First, you need absolute mastery of advanced hardware. The electric heaters, the tungsten carbide brakes, the turbulent jet ignition. Second, you need mastery of diverse energy carriers, efficiently utilizing both electrons and liquid molecules, depending on the exact use case. And third, you need total mastery of digital compliance, the onboard monitoring, the AI virtual sensors, and the cloud-connected digital twin.
And if you are an automaker and you only excel at one of those 3 circles,
You will fundamentally lose market share. The winners of 2030 won't just be the companies who make the most efficient battery cells. The dominant players will be the ones who can flawlessly integrate a near-zero emission combustion engine, a rare earth-free electric motor, and a self-auditing digital twin into a single, highly profitable, globally compliant ecosystem. It is entirely about building massive organizational resilience.
resilience, betting the company's future on technological flexibility rather than a single ideologically pure technology.
Precisely, because the macro environment is too chaotic. If global lithium prices suddenly spike 300%, you simply dial up your advanced hybrid production. If the local power grid fails or becomes unstable, you lean heavily on drop-in e-fuels. If global emission regulations tighten even further overnight, you have an over-the-air software update ready to adapt to the AI sensors. You have to be ready for anything.
It is a genuinely fascinating recalibration of expectations. It feels so much more mature and, frankly, more physically realistic than the pure tech hype of 5 years ago.
It is exactly the difference between a slick Silicon Valley startup pitch and a mature, battle-tested global industrial strategy.
I really want to leave our listeners with a final provocative thought today, something to really chew on after the episode ends. We talked heavily about the car snitching on its own emissions to the cloud. We talked about the massive invisible carbon debt of manufacturing a battery.
Here is the thought I would leave them with. Look at the sheer volume of data processing required just to make the exhaust pipe legal. Are we even fundamentally designing mechanical mobility machines anymore, or are we really just designing hyper-compliant, sustainable digital data nodes that just happen to have rubber wheels attached to them?
Man, that is a deep shift in perspective.
Just think about the reality of the architecture. The car's computer knows its exact fuel chemistry source. It intimately knows its real-time chemical emissions profile down to the milligram. It reports that data autonomously to a government cloud server. It dynamically manages its own complex thermal health. The physical act of moving you from point A to point B is almost becoming secondary to the primary task of proving continuous regulatory compliance.
And for you listening, the next time you get in your personal car, maybe take a second to think about all the hidden emissions we discussed today. It's not just the visible exhaust. Think about the tires microscopically wearing down into the air, the brakes turning to dust, the massive industrial history of your battery pack. It is an incredibly complex global ecosystem you are piloting every single morning.
Indeed it is. The historically invisible footprint of mobility is rapidly becoming highly visible and highly regulated.
On that incredibly thought-provoking note, we're going to wrap up this deep dive. A truly huge thank you to all the brilliant engineers, the researchers, and the analysts churning out these dense reports so we can even begin to understand what the future of transportation looks like.
It has been an absolute pleasure unpacking this data with you.
Until next time, keep asking the hard questions and keep diving deep.